This is the 4.8 and 4.9 podcast. 4.8 is about air resistance and falling objects, and 4.9 just kind of wraps things up for the chapter. So, all right. So what we're talking about here is air resistance and falling objects, and what we're going to see is that air resistance sometimes matters a lot, sometimes doesn't. In this case, anything with a large surface, we're going to see a significant effect of air resistance. But things that are more compact, such as baseballs, rocks, those kind of things, we're going to see less of a effective air resistance. We're actually, in many cases, just going to ignore it for this to simplify our understanding. So if we drop a feather in a coin, you know that the coin's going to reach the ground a lot quicker than the feather will, and the reason because of this is air resistance. And that's going to change the acceleration of these. But if you put them both in a vacuum, and what we mean by a vacuum is something that's devoid of any matter, meaning all the air, so to speak, has been taken out of it, and that means there's no matter. And that's kind of a hard concept to understand, but it's no similar than outer space. There is no matter there. There's no air to push against. And if you drop the feather and the coin side by side, they will fall with the same acceleration, g. It's as the coin and the feather will act the same. I saw a demonstration of this in the Boston Museum of Science, where they dropped rocks and feathers in a vacuum tube, and I could see it with my own eyes, and it was really cool. And also the other thing to remember is in many cases the effective air resistance isn't going to be small enough to be neglected, such as when we're dropping, say, like a ball in a classroom. That's such a small drop that we really wouldn't look at air resistance at all. Although I will try to show you an example with a ping pong ball. Well, it does matter. Now, I threw this picture in, and I'll try to show the video. This is a picture of astronaut Dave Scott, who was on one of the Apollo missions, and he smuggled on board two objects: a hammer. Well, he didn't really smuggle that; they used that, but he smuggled on this, and it's a feather. And here's the actual video of it. There you can see the feather in his hand there. And there's the hammer. And this is a painting done by an artist to represent this moment. And what he did was he dropped the feather and the hammer on the moon, where there is no air resistance at all, because there's no matter and there's no atmosphere. And the two objects fell and hit the moon at the same time. And he actually said, I think the quote was, well, looks like Mr. Galileo was correct. And he was giving credit to Galileo for his ideas. So how does air resistance affect falling objects? We're going to say that it noticeably affects the motion of objects with large surface areas, like a feather, or like you can do a piece of paper. But air resistance is less noticeable when it affects the motion of more compact objects like stones or baseballs. Great test for this is take two pieces of paper, crumple one up, drop them both. Which one's going to hit the ground first? The one with the larger surface area, the paper that you haven't crumpled up. So let's move on to 4.9. This is very quick. So we know this acceleration is the rate at which velocity itself changes. We're going to talk about a couple of possible misconceptions. We don't want to mix up how fast and how far. How fast is we've said is governed by this equation: velocity equals the acceleration due to gravity times the time it's been falling. And how far is governed by this equation: distance equals 1/2 gt squared. And remember, that's a quadratic equation there. And the other thing is acceleration. Acceleration is how quickly speed or velocity change. It's not how fast something is going. Acceleration is how quickly something is changing. It's how fast it's going. And the other thing about this is a rate of a rate. Velocity itself is a rate. And when you're finding the rate at which another rate is changing, you're finding the rate of a rate. And that's why we have that t squared in the denominator of all the equations, and also why we have the t squared appears in the units. So acceleration is not velocity, nor is it a change, nor is it even a change in velocity. So what is the relationship between velocity and acceleration? Acceleration is the rate at which velocity itself changes. And now onto the quiz.